Day number 2 of the operating systems. No, this is, I was just grading operating systems. This is object-oriented programming in C++. So this is the final exam day, and the final exam will be at 3 o'clock today. So on special request, plus also I like to lecture in the morning anyway, we're going to cover a little bit more on pointers, and we're going to cover a little bit more on copy constructors and the use of dynamic memory in classes. Then we'll see how long that takes us, and you'll have the entire afternoon up until 3 o'clock to study and to finish up your assignments. I'm also going to try and give you a little bit of time after in the morning before lunch. So you can work through the lunch if you'd like, or you can work through, I mean, it's a 2-hour lunch. I mean, we can definitely get a lot of stuff done in that to finish up those assignments, because I only have about 4 of them submitted. If you're turning it in and you're working on this while you're listening to me, of the 4, only 2 of them actually got the subject line correct. No, 3 of them got the subject line correct. Make sure you put, if you don't put your student ID on the subject line, and if it's not the first item, I'm not going to be able to use it. So that's the most important part of the assignment, is getting that subject line correct. I think yours, I don't know if yours was correct, but I corrected it for you, because you were like, you're the first person who turned it in, so I think, or second. A couple of the girls turned it in last night. And you got some of it right. I don't need the word student ID, I just need your ID. Write a number. I'm sorting it by your number. So I'm going to sort the numbers in ascending order. Number. Your student ID is a number. Starts out 1, 1 something or other, or 9 or 8 something. Put that as the first item on the subject line. So when I sort it by your number. Otherwise, if it's student something, it's going to show up last, or it's going to show up in the wrong order. If it's a student ID and assignment number 1 and 5 and 12 and 8 on there, it's going to show up in the wrong order. Write your student number. So let me put it on the board. I know I've said it like 3 times, but number, comma, whatever else you want to put on there. Because what I'm going to do is when I grade those final exams, they're going to be put in the order of your student number. I'm going to pull your number out. I'm going to look for your number in the list. If there's nothing in the list, I just put your score in. If I see something in your list, and you can resend me. If you send it to me already and it was in the wrong format, send it to me again, because it's not in my list anymore. It won't show up in the right order. I'm going to order the messages ascending or descending in some sort of an order by your student ID number that's going to show up first in your message subject line. So the subject line, last time I'll say it, has to start out, otherwise you will not get credit for what you're giving me. And I'm not responding back with any confirmations. You just send it to me. It automatically goes into a separate folder, filtered right from my email by your number. Your number shows up. You get credit for it. If I don't see your number in the list, I'm not even going to look for it. It's too much work. Yeah?
I have given student number.
Don't write the word student, S-T-U-D. Don't write that.
82959,
Yeah?
and like my name.
That's perfect. I think you did, a couple people did it correctly. I think, was it you? I don't know, a couple of people who did 1, 4, and 7 did it correctly. So it doesn't really matter, it doesn't really matter what you put in the subject, in the body of the message. That doesn't matter, it's that subject line, and the only thing that matters is you start out the subject with your student ID. That's the only thing that matters, because that's how I'm going to find you. Otherwise, I'm not going to spend, I got like 50 of you. I'm not going to spend too much time looking for you in this folder, and I'm not recording it anywhere. I'm just going to look at the folder, see if you turned it in, take a look at what you turned in, and give you bonus points, 15 points on that final exam. So it's worth the points. All you gotta do is send me it in the right format. Okay, and the only reason why I said that was because of the ones I've turned in, only 3 people or 4 people have got it correct so far. So the rest of them, I don't know. They haven't turned it in yet. They're not in the folder. Okay, because the message filtering looks for a number, it filters it. So it's not even gonna end up in my folder unless you start out with a number. Okay, now I'm done with that one. So don't worry, I won't tell you any more about the numbers. So the pointers. So this one is lecture number 14, and what I'm going to do is start your final exam review prep for you. your study prep, I should say. I gave you the review yesterday, so you know the subject areas that are going to be on the exam. So this one here is called Lecture 14. I'm also going to go over a little bit of parts of Lecture 11, and I'm also going to go over Chapter 14 lecture, little pieces and parts of it, to give you a few more pointers on pointers and a few more information on copy constructors and the use of dynamic memory. So stop me as we go through this. This is really review for you, and with a more iteration of some points. So C++ is really one of the very few languages. Java uses pointers, but doesn't have that asterisk symbol. So we don't have like direct pointer usage, but we do have pointers. So the concept of the pointer is very C++ish. Excuse me. A pointer variable, or just pointer, contains the location of the memory, or the address in memory, or the memory cell. So by using a pointer to a particular memory cell, you can locate the cell and determine its contents. So here's some examples of some pointers. You can declare pointers on more than one on one line. So I have integer, and remember I said before that little asterisk is the pointer symbol. So whenever you see that, you're working with a memory address and not a value. So it's called a reference variable and not a value variable. And the pointer symbol, that one's called a reference, and then we have a dereference. It's the same symbol, it's just used in different contexts. So this one as a reference shows up somewhere between the data type and the name of the variable. So it can show up on the right, it can show up on the left, or in the middle. It's your choice. Once you declare the variable using the pointer type, then you just use the variable as if it were a memory address. So this one says Q is equal to 1, 2, 3, 4. So you've assigned 1, 2, 3, 4 as a memory address for Q. Well, how do you know you got 1, 2, 3, 4? That's very odd. You're not going to be doing that because programmers don't get memory addresses. So if you see a line of code that's assigning a memory address, a red flag right there, that's pretty bad. We don't do that. Instead we use the ampersand to say the address of something else, or we say new, give me a new int. And if I say give me a new int, I get the memory address out. I can actually print the memory address to the screen if I want, but it doesn't really mean anything to me. It's just a memory address, and sometimes memory address might change throughout the program execution, depending upon where the runtime is actually storing that data. So pointers give us what's called dynamic memory allocation, and the pointer can point to a memory area and allocate it at execution time. So here's some examples. So we have integer p, and then we have p is equal to new int. You can do it on one line. You can say integer asterisk p equals new int, or we could say in 2 lines. We've got it here. So this is the reference. This is the allocation of a new int. Notice there's no opening and closing parameters or anything because int's the data type. So we're using int as the data type, and we're saying new int, new float, new double as a piece of information to store a variable of that particular data type. So follow p, have it equal to 1, 2, 3, 4. Well, hopefully we have a memory address 1, 2, 3, 4 out there. Or delete p, which is going to delete 1, 2, 3, 4. It doesn't actually delete p though. And then on the right hand side we have the array concept. So we have integer asterisk p, p is equal to new int, but we have 10 new ints in this particular case. So we're creating an array of 10 ints. And then we're going to follow p plus 2 and have it equal to 1, 2, 3, 4. Well, that's going to be p plus index value. If it starts out with 0, we got 0, 1, 2, 3. So it's going to increment it to the next integer plus 2. And then P1 is going to be equal to 2, 2, 2, 2. Well, that doesn't make any sense either, really. It's just a memory address. So, I mean, it does make sense. It's legal code. But you're never really going to assign P a memory address. You're going to use the address of something else. So if we look at the location of 342 for what we want down here, and let's say, for example, the starting address was, in this particular case, 340. We can have 340 as index value 0, 341, 342, 343. Do we know these addresses? No. Do we know the increment by integer value? Sure, we do. It's just the increment of the array indexes, 0, 1, 2, 3. So if the pointer P is pointing to this address, then we can use it as a, anything, just like we've normally worked with, any piece of data. We can use it the same way. So here's some information for you to kind of get a feel for what's going on, and this is what you're going to see on the final actually, are little boxes with information in them. So this is a good slide set actually because it represents the format you're going to see stuff in. So I have integer pointer p, comma, pointer q. Well, what does that do? It gives us a p and it gives us a q, and then we have garbage in there. And then we have integer x. So we have an integer over here that says x on it. Now you notice, and this is not, this was made as a true to illustration, these two spaces are smaller than that space because this space is holding an integer value and this space is holding a memory address. So it's going to hold a memory address of an integer value, but the pointer space is a different format. It's going to hold a memory address. We need something big enough to hold a memory address because that's what p is going to be holding. So it's not holding the same size space as x. X is going to be holding an integer space. Then we can say p is equal to the address of x. P doesn't get x. The content of x doesn't end up inside of p. Instead, what ends up happening is p now over here is pointing to x, or it's also the asterisk p. So x or the asterisk p is now being represented by this little x space over here. So we have the big space, and then we have the little pointer space pointing to it. And then we have follow p and have it equal to 6. Well, so if we follow p, then in this particular case, x is now equal to 6 because x and p are pointing to the same memory location. So it's really the linkage that you really want to be concerned with when you start looking at pointers and working with pointers. And it's the linkage that causes the most problems. So if you don't have the linkage correct, what ends up happening is then you're going to have, or you have multiple things. You're going to have either a memory link, or you're going to have a dangling pointer, or you're going to have some really bad logic. Actually, also in the area of linked lists, you end up with lost components, lost nodes, because you lost a part of the list and the rest of it just went away because it was all linked together that way. So getting back to the concept of the linked list, if we create a bunch of pointers and we put a bunch of memory addresses in those spaces that are holding the pointers, then the spaces themselves are keeping track of each other. So that's the interesting part that makes another part that makes a linked list different from an array or an array list, is that the linked portion, the data for the linkage is actually stored at the memory locations. It's not stored outside of it. An array, you've got a structure where the data for where to find the items is stored outside of the actual storage of the data. It's stored in a variable. Linked list, we don't have variables that represent the list, and we don't have a structure that represents it. It's those little memory pieces that are keeping track of each other. So that's another difference between a linked list and an array list. And you want to know the differences between that because there's several questions about the differences between linked lists and array lists. That's one of them, actually. So declaring a pointer variable. And so we've got 3 different scenarios here. We have A, B, and C. And A, which is up here, declares a pointer variable. So if you need some examples, some help in terms of your review this afternoon before 3 o'clock when the final starts, this is lecture 11. And we have examples of, as in the case here, the declaration of the pointers, the pointing to statically allocated memory. We know that X is a statically allocated memory component, and we know that these guys are dynamically allocated memory. They're static because when the program compiles this, when the compiler goes through and says, oh, integer X, it predefines a space out in memory, puts an X label on it, and statically allocates and binds it. Anything static is done before runtime. So it can be done at compile time, language design time, anytime before runtime. Anything after runtime is all dynamic. So it happens in, well, I should say real time because there's nothing really real about that. But it happens during runtime. So here's the pointers, and then we also have the concept of assigning a value. And we're going to have attendance. Okay, so let me pause this for a second so we can do the attendance. All right, let me finish this lecture. So I was talking about pointers, and anyway, so I was giving you the legend on the bottom of the slide where A was declaring a pointer variable and B was pointing to a statically allocated piece of memory, And then C is the assignment, so assigning a value. So following P and having it equal to 6. So if I printed out X, I'm going to get 6. That's going to print to the screen in this particular case. And then here if I say if P is equal to a new int, X is not garbage, by the way. X is not inaccessible, X is not a problem. Even though P was pointing to X, and then now we said P is equal to a new int, well, X was still X because of this whole integer X up here. We didn't actually create garbage with that. So when you get the final exam later today, you're going to see scenarios that are going to be like, well, but if something is pointing to it, then it's not garbage, it's not inaccessible, it's not a problem. We can have a pointer point to anything we want to have it point to, and we can have multiple pointers. So if you just remove one set of the pointers, no problem. You know, that's not causing a problem at all. So don't be afraid to think about the scenarios and determine if there is a problem or if there's not. This does not cause any problems at all because X up here was declared as an integer X.
So it is on the stack, so that's why.
It's a statically allocated piece of memory. It has an identifier called X that identifies this memory address. We just pointed to it. We said that P was equal to the address of X. So we have X and P pointing to the same thing. Well, if I said P is equal to a new int, no problem. P is now equal to a new int. It's not pointing to X anymore. That's not causing a problem at all. So I guarantee about 50% of this class will answer, oh, it's a memory leak. Like, no, it's not. So that's why I say don't be afraid to look at the scenario, just because it's going to have you, it'll be a couple of multiple choice questions that will have you think about, is that causing a memory leak, a dangling pointer, blah, blah, blah. Because, you know, what if I had Q and P were both pointing to the address of X? And then I had P is equal to new int, and then I deleted Q. I still have X. You can't delete X. I can't delete X through Q. It doesn't work. Why doesn't it work? Because we're mixing static with dynamic. X is a statically allocated. Let's go back up here again. And there's a reason why I was talking about static. Rule number 1, dynamic works with new and delete. Static is controlled by the stack entries and is controlled by the compiler. You cannot delete static data. It does not work. So if I have a pointer and I point it to the address of X and I delete the pointer, I have not deleted X. X is still around. That does not cause a dangling pointer. However, if I made P is equal to new int and I deleted P and I said P is equal to null, that's not a dangling pointer either. A dangling pointer is when P is going to be equal to new int, then I delete P, but I don't do anything with it. P is still equal to this new int, but I've deleted P. P is still around. I can still use P. I didn't remove P. I removed what P was pointing to, which was that new int. That's okay. That's what you have to do, actually, to get rid of the memory. So if that's the case, nothing wrong with that line of code at all, actually. When you go to access P, if P doesn't equal null, that's a problem. Because then you're going to say, well, I'm using something that I allocated and I deallocated it and now I want to use it. That causes a problem. So it's not really, it's not dangling if it's set to null. So a lot of people in their code would just go P is equal to null right after it. So you don't have any problem at all. So when you write your code, you're going to check to see is P equal to null? If not, if it's not equal to null, then let's do something with it. Because we have two cases. It's equal to null, which means it's not valid, or it's not equal to null and it's valid because we haven't deallocated it or something like that. So those are just kind of the common scenarios. But no, you cannot delete static data through dynamic pointers. It doesn't work. You can try. You actually will get an error message in that case. Well, you'll get a runtime. You might actually get a memory violation. It'll say something memory violation or memory something or other at x dot something or other. Those really weird code messages that show up, the cryptic messages that don't make any sense. Because you try to delete statically allocated data, the program only has access to the dynamically allocated data, which is at the heap section, right next to, above, the opposite end of the process as the data section. And you're trying to delete the data section, it's going to say protected memory error or something, or no, memory inaccessible, or memory not available. can't delete that stuff. That stuff's controlled by the stack entries. Anyway, long story short, it causes confusion. So, all right, so here's some more examples where we can follow P and have it equal to 7. So we said, up here we said P is equal to a new int. X is still equal to 6. So we have X is equal to 6, and we follow P and had it equal to 7. Just because P was pointing to X at one particular moment in time doesn't mean it's still pointing there. It's not pointing there anymore. When we say new, it's no longer pointing. So keep in mind, new is creating a new memory address, not pointing to X anymore. So P is equal to Q. Is that legal? Sure, why not? They're both pointers. Pointers can be assigned to each other. So if I said P is equal to Q, or Q is equal to P, sorry. Now P and Q are both pointing to this guy over here. What's this guy called? He doesn't have a call. He doesn't have a name. It's nameless. There's no such thing as a name. This guy's called X. This guy does not. These guys don't have a name. Oh, it's one. It's actually, because it's 2 lines, it's one memory address. It's a new int. So if you want to say anything, it's a new int. A new int. Well, a new int's a memory address. And we happen to have P and Q pointing to it. So we could follow P, or we could follow Q and get to the same memory address and change it through both of them. This is what linked lists are doing, actually. They're just following. And then we have one piece that's following another piece that's following another piece that's following another piece. So in D, E, and F, D is the allocation of dynamic memory, and E is assigning a value, and then F is copying a pointer. So you're never going to see any examples that say, you know, follow P, have it equal to the address of X, or no, P is equal to the address of X is what you're going to do, and then delete P. You're not going to see that in any textbook example. You're not going to see that anywhere because you're deleting static memory through a dynamic pointer. It's just not right. It just doesn't work. Actually, what will end up happening is you'll end up, hopefully, with compiler error before you get that runtime error. So here's some more examples. We got number G, H, and I. So G is allocating memory dynamically and assigning a value. H is assigning the null to the pointer, and then D is deallocating the memory. So what do we get? Q. So P and Q were both pointing to that other new integer. In the last we saw P and Q. Excuse me, because we said Q is equal to P, and when we do that, they're both pointing to the same memory address. So now we say, well, let's give P and Q their own memory addresses. So here we go. Q is going to be equal to a new int. P already was pointing to 1 with a new int. So when we said Q is equal to P, they're both pointing to P's. So let's go Q is equal to new int. We do that, we get one over here, and then follow Q and have it equal. Oops, we got our Q's down here. My P's and Q's are backwards. So we go down here, and now we say follow Q and have it equal to 8. So now P is 7, which is what we had up here. We still got the same. P. P didn't change. It's the Q that changed. And we still got X out here, and X is still equal to 6, is what we had in an earlier example. So now I can say P, if I said P is equal to null, right here, what is that doing? Yep, creating garbage, because this is now inaccessible. So I should have deleted it before I had it equal to null. When I say P is equal to null, P is no longer equal to that new int that I created. Nothing else is pointing to the 7 that's sitting here. It's empty, there's nothing else around it. That's how you can make garbage with null. So just because you see null in there, don't assume, oh, there's no garbage. If I assign the pointer before I delete the information it's pointing to, I'm going to create garbage 100% of the time. If I delete Q, then I've deleted the memory. But Q is still around, so I say Q. So this is the proper way of doing it. Delete Q, Q is equal to null. So I could have deleted P, P is equal to null, and I wouldn't have had this piece hanging around. So now I have the piece hanging around because I didn't delete it first. Once you assign the pointer to something else, you don't go back. There's no history. So the only way to retain some, well, the only way to retain some sanity in terms of what it's pointing to is to make it equal to null. Then you know it's not pointing to anything valid. But P is still around, and so is Q.
So the delete statement, it will delete the memory it's been pointing to,
yep.
Not the pointer.
Correct. The pointer variable is still around, so don't fall into that trap. I can use P, because then a lot of people, if I did this on an exam, I said, delete Q, Q is equal to null, Q is equal to new int. And people go, oh, no, there's something wrong with that, we deleted Q. How can Q now be equal to a new int? You don't delete, you're not deleting Q. You're deleting the memory address that Q's holding on to. Once you create Q, it's around for life. You can't get rid of Q. Ever. It doesn't go away. Well, maybe it'll go away when the program ends. Or it should go away when the program ends. But for the life of the running of the program, Q's around forever. So is P. So is X. X doesn't go away either. It's a variable.
So X goes with the stack, like program will go.
Yeah.
What pointers is P and Q?
P and Q don't go with the stack either. They're dynamically allocated. So when you say integer up here, when you say integer P, integer Q, and you use this thing here, it makes the life longer than this actually. So the pointer will stay. However, I should point out that scope rules still apply. If I did this in a function and the function goes away and I come back to main, this will go away. The news don't go away, the variables go away. So in this particular case, if this was all happening in a function and I went back to main, this new int's still around. Nothing's pointing to it anymore because the variables that were declared were in that static scope of the function, and now the function's gone away, so those variables don't exist anymore. What happens to the function stays in the function. We return back to main. It's like, where's P and Q? Well, we can have a different P and Q inside of main. So then people, well, that's why you'd pass the reference back out of the function. You're going to pass the reference so that you can say, keep track of P and Q when the function's over with. Otherwise, you're going to lose the pointers to the function, to the memory that you allocated. That causes a memory leak. So, which is actually kind of interesting because you can dynamically create objects in the function, and then when you leave the function, those objects will be deleted automatically because you've statically referenced them in that function, and you come back to main, and then you go, well, what happened to the memory that those objects were allocating? That's what you need the destructor for. So that when the object is removed from memory, all the memory that the object was pointing to is also removed. So the destructor removes all that memory, which is the purpose of that. So I'm going to review the destructor and the copy constructor in a few minutes as well. So let's see what we had here. Back at the ranch, we got the P and the Q, and they were equal to each other. And then we decided to give Q its own memory, and then we said P is equal to null, and we created some memory leak there. And then we deleted Q, and we had Q is equal to null, and we said, okay, this works better this way. So the null always comes after the delete. If you put the null before the delete, or if you put a different assignment here, if I said, in this particular case, I didn't actually have to say P is equal to Q. I could have said, okay, now P is equal to the address of X. Then I would have lost this new int as well, because I'm not pointing to it anymore. So A, we got P is equal to new int. P is equal to new int. So if I printed out what's at the address of A right now, what's at the address of P, I get garbage. In B, I say P is equal to Q. So Q is equal to P. I'm saying this backwards for some reason, because I'm reading this like a P and this is like a Q. I don't know. I'm not used to looking at typewriter font, I guess. Anyway, long story short, they're both pointing the same. I delete P. I say P is equal to null. Q is still pointing to that. So Q is still pointing to whatever P was pointing to. This is what we get with the linked list, by the way. We create a bunch of memory. We assign a bunch of pointers to the memory. We move them around. We don't move the memory around. Which is actually kind of the interesting thing I was pointing out yesterday. When you ask students to reverse a list, and they start creating new everything, and it's like, well, why are you creating new memory when you're just going to like read the list in a different order? We shouldn't be working with these guys out here that are pointing to the memory. So there's no really, which makes a linked list more effective. So let me go back to linked lists as another comparison between linked lists and array lists. Linked lists deal with data a lot more efficiently. It doesn't move anything around. It just points to it. So if the list is a structure that you're using to go count or to point or to order, and you're just making the memory order each other, there's no overhead. There's no moving. You want to move something, you want to move an item in the list from this position to that position, you just change the pointers, you don't move any memory. In an array, you actually have to pull the memory out of one location, copy it over into another location in order to get that memory moved. So in an array, the running time of the operation to actually copy or move the data, much more expensive than a pointer change, which is a lightweight. Okay, now it's not this address, it's that address. Okay, you're just switching the addresses around on a pointer instead of picking something up, which is the same argument you say with pass by value versus pass by reference. By value, you're sending a whole value, you're sending information data to a function. You're sending the data, so you got to make a local copy of it inside of that. It's called a shallow copy when you do that. I'm going to go over shallow copy and deep copy in a few minutes as well. And then inside of that function, you use the shallow copy so that you don't change the original value. And it's a fake. It's like a photocopy of that value that you sent over there. That's time consuming. More time consuming than sending a memory address and using what's called, it's a deep reference, because you're using, it's pass by reference is when you send the memory address to the function, and inside of the function, instead of using a copy of that data, you're actually going to the memory address and accessing what's at the memory address. And then we have what's called a copy constructor on an object. So you send an object, you sent an object by reference over to a function. It comes in by value. It makes a shallow copy. Well, what's it making a shallow copy of? The same memory address. So it takes copies of memory address and it says, oh, we're 1, 2, 3. Now we're 1, 2, 3. It's the same memory address. So the copy constructor on an assignment, on a copy by shadow, a shadow copy operation, it makes what's called a deep copy, which isn't a real copy. So a shallow copy is an identical copy. If this object was pointing to a memory address 1, 2, 3, the copy is also pointing to address 1, 2, 3. But you could possibly imagine if I have the original and I have the copy and they're both pointing to the same memory address, 1, 2, 3, one's not really a copy. They're both the original. So if you really want to make a copy, then you invoke a copy constructor. Makes a deep copy, which isn't a copy. It's like the reverse psychology of objects, because so now you say, okay, I'm going to make a copy constructor so that when my object is copied, so now I take the copy, now I said same scenario, take the object, make a copy of it, and now they're, without the copy constructor, they're both pointing to memory address 1, 2, 3, because they're both using this object that was allocated dynamically. So yeah, okay, I'm going to make a deep copy. Well, deep copy goes out into memory, dig out a hole, a new hole, stick what's in 1, 2, 3, and call it 4, 5, 6. So now, original is pointing to 1, 2, 3. Copy is pointing to 4, 5, 6. Not the same memory address. So are they original and the duplicate, are they identical copies? Nope. It's a copy, but it's not a copy. It's an original copy. So long story short, that's what's called a deep. They call it a deep. Shallow is on the surface, takes the memory address, copies the memory address. Deep goes below the surface, digs out a new hole of memory, puts another label on it, sends the label back. So it goes down below the surface, which is why they call it deep. Goes into the memory, actually go into the memory, take what's in the memory, copy it to another memory location, and then send back the address where it's located now. That's a deep copy. So shallow copy, deep copy, you make a deep copy by invoking a copy constructor. You don't get a copy constructor by default that does a deep copy. The default copy constructor that does exist does a shallow copy. Most cases, shallow copy is just fine. You don't need to do a deep copy unless you're allocating memory inside of that object. If that object is never allocating any memory, you don't need to do any deep copies. This is a waste of time, actually. What are you going to copy? And I'll show you, I'll review the copy constructor in the next lecture here, that you actually create new this, new that inside of it. Well, if you don't have any original news, why do you need copies of news? You don't. So it's kind of a no-brainer when you go to create the copy constructor. You figure out if you need one when you start to figure out, well, what am I going to put into this code section? I don't have anything to put in here. Well, then that might be a red flag telling you I don't need to make a copy constructor. So, all right, so an incorrect pointer to a deallocated node exists in this example here, where we've got 2 pointers, integer pointer p and integer pointer q, the same two we were working with before. So we created the 2 of them. And then now we have p is equal to a new int, so we allocated a new int for p. And then we said we followed p and had it equal to 1. And we still have q out here. So p and q, but q never got assigned to anything. Q didn't get a didn't get a new int like p did. So q's still here. And then we said, well, q's now going to be equal to a new int. So now q is pointing to something. If we've created a reference, in this particular case, where we have integer p and q, and they're both pointer variables, we gave p something, and we still have q. What's q? Huh? Not a dangling pointer. It's not initialized. It's the declaration without an initialization. It's an uninitialized pointer. So if you try to use it, the compiler comes back and says uninitialized. You didn't assign a value to it. That's the same error message you get if you say integer x, cout x. It's going to say, well, you declared it, but you didn't initialize it. You didn't say x is equal to anything. Well, I didn't say q is equal to anything. Until I say q is equal to something, I haven't created a dangling pointer. I have an uninitialized reference. So, but yeah, that's not a dangling pointer. So let's see. It's not really even a pointer at all because we haven't done it. Well, it is a pointer, but it doesn't reference anything. So, not initialized. Some languages initialize it to null. C++ does not initialize, which is kind of the most bizarre thing. In fact, some languages like Java, if you said integer x and you cout or system out x, you'd get 0. You did that same code, integer x, and you cout x in C++, you get, if you don't get an error message in the compilation stage telling you that you've got a declaration without initialization, then you'll get garbage printed to the screen because it's not initialized, which is kind of terrible actually when I think about it. Java initializes everything automatically. C++ doesn't initialize anything, not even objects. So you can make a reference pointer to an object and use the object and it's never been initialized. So it's just not what I'd call a safe language, going back to that concept of security or safety in language. Alright, so I'm going to say q is equal to the new int. So now I've got p and q. They're both equal to a new int. But I haven't really assigned a value, so let me do it. Follow q, have that one equal to 2. So now p is equal to 1, q is equal to 2 when we followed it. Cout follow p. And then the outline contains 1 and 2. Well, because we're going to cout, this is a word wrapped, I'm sorry. Cout follow p and follow q, we get 1 and 2. Follow p and have it equal to follow q plus 3. If I follow q, and q is equal to, well, what is q is equal to 2, plus 3 is 5. So the value turns into 5 for p. And then cout to follow p, now I get 5 and 2. So it's just an example of a way that you can program with numbers. So you can follow it and do addition to what you follow with. Anytime you dereference the pointer variable, you can use it any way you use any other piece of variable in the language. So now we can say p is equal to 2. Now we've created garbage. We've got an inaccessible object out there because p was equal to this memory address that was holding up 5. Now it's holding up, now nothing's pointing to the 5. But the 5's still out there. And now if we cout follow p and then follow q, we get 2 and 2 because they're both pointing to the same. If I follow p and I have it equal to 7, and I print out q is going to be equal to 7. So now because they're both pointing to the same thing. 5's still out there. 5's never going to go away. It just stays out there until the program ends. Follow p and now have it equal to a new int. It does not get equal to the old one. It's still the new. It's brand new. So why didn't they just fix this in the language? I don't know why. All they could have done is put a little error message in there. It says, hey, you're leaving a piece of garbage out there, right? You know you're causing a memory leak. And the program went, I am? Well, I didn't mean to do that. And then we would have fixed it, right? So, kind of odd. There's a lot of things about the language that, if you think of the concept, okay, so if I were to go back to what I was saying yesterday, Dr. Reel's class, comparing all these different languages, I seriously think he should teach that class. He would be good at it. He knows more languages than I do. We take and compare C++ and Java. Most people go, oh, there's no pointers in Java. The entire language is pointer based. The entire language is dynamically. There's no such thing as static data in Java. So it's this, what you're looking at here, without the pointers. So someone did fix it. So if you do this in Java, garbage collector comes around and picks it up. So, ooh, no more reference. Actually, do this in Objective-C, garbage collector comes around and picks it up. You do it in C++, your program crashes. But Java is all about pointers. The entire language is, everything is passed by reference. Everything is pointer based. The entire language is dynamic. There's no such thing as a stack in Java. But there's no pointers. So it's like the best language out there, I think, really. Makes efficient use of everything. However, the programmer never has to actually worry. The programmer never even hears about a pointer. You don't hear about pointers until you take C++ and you go pointer, or C and you go pointer. I don't know. The problem with Objective-C is we have pointers. So Java is 100% no reference dereference symbols. No symbols in Java. In Objective-C, we got the symbol, but we don't have all the headaches of C++. So, although the language is cryptic in terms of its syntax, Objective-C is an easier language than C++ to program in. It's just different syntax. So, for some of you who are taking my Objective-C course next term, which some of you might be taking because it's offered on the weekend, you'll like that language. That language is fun. That language doesn't have all the hang-ups of C++. It's a better written version. So it's in the same family tree. So you have C, and you have one branch that says C++ on it, and another branch that says Objective-C on it. But they're both the same. They're just two different implementations of object orientation built on top of C. And then we have Java. That's not related at all. Java's like way over here. And Java is C++ plus all the bug fixes. So Java is a bug-fixed version of C++, and without all the confusion. They took the confusion and the lack of orthogonality and all the rest of the crap out of the language, and they made a better language out of C. Java is just a rewritten version of C++. Objective-C is a totally different implementation of the same concepts, which makes it kind of an interesting language. If you know all three, you'll never be out of a job, because those are really three popular languages. Throw a little Python in there. Python's easy. Extremely easy language to learn. Then you got job security for the rest of your life, actually, if you want to work in this area, because then if you know the differences, then you look at the code, you can fix problems easily. And then the more languages that you know, I encourage you to learn more languages, because the more that you know, the more that you can see the flaws in the different languages, and the more that you can actually troubleshoot better, because you see, oh, this one needs this, and that one needs that. And then knowing one language helps you understand the other language. And then the more you know, the more you can understand more. It's like people when they learn foreign languages, spoken languages. You learn one Romance language, you learn them all. So I say learn Spanish. Then you can pick up Italian, you can pick up French from that actually, really easily. It's actually just different pronunciations, but I'm not a language expert when it comes to spoken languages, so I'm not going to cover the linked list stuff, but if you want some, you do not have to implement a linked list on the final exam. However, the node concept might be on there in terms of a multiple choice question, as well as a couple questions about linked lists versus array lists. The other thing you want to remember, and because I am talking about pointers right now, and I saw this yesterday, I don't know where the girl went. No, it was you, who was using this symbol in a non-pointer scenario. And I went, that's like the weirdest thing in the world. Traditionally, that symbol is only used in replacement of a dot. But the dot wasn't working on her system, so she was using the arrow. I'm like, well, are you making a pointer? On yours either?
When you use this.
But when we use this, it was working everywhere.
Yeah. Odd.
Yeah.
Odd. But anyway, long story short, the only difference between pointers and non-pointers when we get to structures and classes is that the dot notation in a pointer implementation turns into an arrow instead of a dot. This you have to use, with this you have to use the arrow because you're referencing this as an object. This is dynamic. It's not static, it is dynamic. But if you said P is equal to my person, or new person, that's dynamic as well. So maybe you were using dynamic memory in there? Is what I'm thinking? Well, this, if you had said this, that would have been dynamic.
It was only with this.
Yeah, only with this, but otherwise it was what this new value, then only we use error. But if the object relation,
Yeah.
that
Well, bottom line, the way it's supposed to work is if you're using new and you're creating dynamic memory, you're using an arrow. If you're not creating dynamic memory, you're using a dot. This is dynamic though. This is a reference to the memory of the individual object. So that is an arrow case. If you're using this in C++, it's an arrow. In Java, it's a dot, which is the most confusing thing. Or then we have, or is it self? No, self is, oh my god, self is Java. Self? Super, we have self as well. Not in C++? Then it must be Java. Huh? Not Java? Self must be Objective-C. We have ways of identifying objects as our self. Some languages use the word self, some use this. Everybody uses super, because super is the one above us. Nobody uses sub. Instead, it's this, self. You know, it's basically the reference to itself. So I want to say Objective-C uses self. I can't remember right now. But I think that Java and C++ are probably both using this, actually. So in Java, you're calling the constructors with super. And you're calling the constructor as the first line inside of the constructor or inside of a method, actually. You can call super as the first line of code. In C++, we don't have that syntax. In C++, we overload the constructor by specifying specifically which constructor we want from the base class on the signature line of the constructor. I'm actually going to get to that. Let me get to that, actually. So I'm going to stop this here. I don't think there's anything else in here outside of all of the pointer node stuff. Variables. You don't have to know all the linked list implementations. So let me end this for a second here.